we have to talk about refraction a bit more because it's kind of a more in-depth, complicated light interaction than the law of reflection is. So let me just recap where we are at the moment here. So we're sort of saying in our analysis here, in our discussion, that we have some material here, might be like a big vat of water or something like that. And this might be some air up here or something. And what our concern is then, if we have some light ray coming in like this, so here's our light ray coming in like this, we know it's going to encounter the normal right here, like that. And we know the law of reflection, which is pretty simple. Is going to say, well, the ray's just going to go out like that. And we know something about the angles here. We know that theta 1 is equal to theta 2. And that's just the way of law of reflection is going to work for us. And we know then that there's the law of refraction, where the light ray is going to go bend in like this. And it's the bending law that we're discussing. So right here at the interface, it bends. It no longer carries on that same direction. It bends in like this. So you can get everything labeled up here if you want, like this. That's the reflected ray. And that's the refracted ray. So the question in this video here that we're going to have to get out then is, well, we know theta 1 is equal to theta 2. That's the law of reflection. But there's another angle in here that we can call theta 3. So this angle like sitting right in here. See, there's the normal and there's the refracted ray. What is that angle in there? And how is it dictated? And is theta 3, that refracted angle, is it related to theta 1 at all? Is there some correspondence between them? That's sort of the question in front of us at the moment. Now we know from the law of reflection that theta 1 is equal to theta 2. That's all taken care of for us. But if we choose some theta 1, like maybe this angle or shallower or steeper, how does the refracted angle depend on that, if anything? Well, in order to answer that question, I have to introduce you to something called the index of refraction. The index of refraction. So what the index of refraction is then, it is a number assigned to all materials that tells you how much it can refract light, something like that. So it's a number then that we assigned all materials that basically tells us how much it will refract light. And by refracting here, you might also replace this word with how much it can bend light. In other words, different materials can refract or bend light in differing amounts. So that's our first clue right there. So if I go back to the sort of the original issue right here, is we're trying to nail down what theta 3 is going to be, the refracted angle. Well, it depends on numbers that are assigned to these materials here. So let's give you a few numbers. So we're just going to make a little table here. So we're going to call this column what, and we're going to call this column n right here. And n is the scientifically reserved symbol most of the time for this thing I'm telling you about, the index of refraction. There it is right there, n. Okay, so what we'll start then, it'll start with a vacuum. And what a vacuum means is really just when there is absolutely nothing there at all, like outer space. Okay, the vacuum of outer space. There's no air, there's no glass, there's no water, there's no anything. The index of refraction of that is 1.000. So there you go. So the first thing you get is the indices of refraction are always 1 or greater. They're never less than 1. So we'll start there with a vacuum. Then, of course, the next thing I can think of here in terms of index of refraction would be air, sort of the next thicker thing after the nothingness of outer space. Well, that's going to have an index of refraction of 1.0007. So you can see that it gets just a tad bit higher. So the nothingness of outer space and the seemingly nothingness of all the air around us just adds a little 7 in there. Okay, but of course you can get thicker materials here. Like say you encounter some water, which we saw the bending of the duck and the polar bear and the lower halves of those people in the water here. Well, that's going to have an index of refraction of 1.33. Okay, and going on then. Oil, like you might cook with or put in your car, something like that, would have an index of refraction of 1.47. And there's glass, which is always associated with light and working with light, index of refraction of 1.5. Then, of course, there's a diamond, index refraction of 2.4. So we can go on, but we'll stop there. We can get plenty of astronomy done just with these here. And let me just point a couple trends out on the table here. In particular, you can see that generally as you go down this way here, you get denser materials. So as you go from, like air is thicker than a vacuum, water is thicker than air, oil is thicker than water, glass is thicker than oil, diamond is thicker than glass, that kind of thing. So you can say denser or thicker. And by thicker, I don't mean like how wide it is, how thick a layer of it is. I mean, it's like how thick the material seems to you. Like you can very easily wave your hand through air, but not so easily through water, that kind of thing. So these numbers here, these indices of refraction, are what's going to allow us to figure out what that theta 3 is going to be, as I'll show you then in the next video.